Okay, so I'm going to go over page 12 either because you missed it or you want to recap it. And this is predicting the products of single replacement and double replacement reaction. So this is kind of a continuation of the last podcast that you had, and that was predicting products of combustion, synthesis, and decomposition. So by finishing single replacement and double replacement, we can now predict the products, or after this podcast, this recording, we're going to be able to predict the products of all reactions. And I'll just tell you what I'm mixing together, what I'm doing with it, and you'll be able to tell me what I'm going to make. So let's get started. At the top of the page 12, it starts off talking about single replacement reactions. First, kind of want to remind you what they are. There's an example of this general equation here, reminding us that single replacement reactions, we called it the homewrecker reaction because there's some single element in this situation. It's going to be a metal element, and that element is going to replace part of the compound that's with it on that reactant side. So we know it's single replacement if I have an element and a compound as our reactants. And what we need to do is figure out what part of that compound does that element want to replace. And so in this first type, and you'll see there's another example with halogens down below, but in this first type, when we're working with a metal being our single element, that metal is going to replace the first element in the compound because metals like to have positive charges. So when they come over and react with this compound, they're going to replace the part that has the positive charge so that that positive charge can get with the negative charge. So the metals are all fighting over these anions, these negatively charged pieces. And so in this first situation, magnesium and iron both want to get with nitrate. And that's, all well and good. Elements don't really have feelings. They're not really fighting over it. But there is a difference in their compatibility with that nitrate and how much kind of nitrate wants to be with one of them. And just like any reaction, we called this the homewrecker reaction, which isn't a fun, happy analogy, but it happens. And with elements, just like with people, that change, that breakup isn't going to happen unless the person that they're breaking up for is worth it, if they've got something going for them. So everyone wants to trade up, which is why we have the activity series. And you don't have to memorize this. This is on the back of your periodic table over there at the far right side, the opposite side from our polyatomic list. So it's there. It just has the names instead of the symbols. But this is a list of the elements in order of kind of their attractiveness to other elements. So Li is at the top. It's the most attractive. Anyone and everyone will break up with their current partner, their current compound, if lithium is available. So this is just a list. So when we're doing a single replacement reaction, we need to look at this list of priorities to see if the reaction, the change that's going to happen, is a favorable one, if this anion is going to be trading up. So in our first example that we're doing together, we said that we were going to be comparing magnesium and iron, Mg and Fe. And so if we look in this list, I have my Fe here, and Mg is up here. So because magnesium is higher up on the list, that's the element that's going to get the girl. That's the element that's going to be part of the compound. And if we go back and look at our compound, that's not where it was. So this nitrate would rather be with magnesium than with iron. So we're going to go ahead and make that change happen and put magnesium with the nitrate. But just like any time when we write a compound, we have to check the charges. And magnesium is a +2 charge, and nitrate is a -1. So we do have to cross-drop reduce, bring that 2 over onto the nitrate. And that's our magnesium nitrate. Now that's not all we're making, because remember, that magnesium replaced the iron. So now our iron got kicked out, and he's on his own over here after the reaction. He's single. So that first example, this is our products for this single replacement reaction. So when we're doing these, we just have to check, figure out who's trying to switch, see which one is higher up on the list, and that's the one that's going to be in the compound. So in this next example, my metal, Cu, is going to be trying to replace this zinc, Zn, but when we look at them on the list, I've got Cu here, and Zn is higher up on the list. So that chlorine would rather be with zinc than with copper. So, and it's already with zinc. So because it wants to stay with the element it's with, there's not going to be a reaction here. And there's a couple different ways you can show me this, but you have to be very clear. Don't just leave it blank. You could write out no reaction. I'm just going to write NR because that's easier. Or if you do leave that blank, at least cross out the arrow because that shows us that it's not going to move forward. It's not going to react. So single replacement reactions don't always happen. It has to be a favorable reaction. It has to help make that compound more stable or else it's not going to happen. So I'm going to do this third example with you too, but then I'm going to leave those last 2 or 3 for you to do. I might do one of them. So looking at what elements do I need to check on my list? Magnesium and hydrogen. Looking at my list, magnesium is higher up. Magnesium is up here. You see it says H2 in the list just because that's what hydrogen looks like if it was on its own. But you don't have to have like H2Cl to use it. That's just hydrogen. And like you see on the back of your periodic table, it just says hydrogen, so it doesn't matter what kind. So magnesium is higher up. So magnesium is going to get the chlorine. Going to put them together, and just like up here when we did the magnesium nitrate, magnesium has a +2 charge. So we're going to bring that over, and then the hydrogen is by itself, a single now, but he's got a buddy because hydrogen is a diatomic, so it can never be by itself. So that is our final reaction. Now, I'm not balancing these because I'm focusing on predicting these products, but these all could be balanced fairly easily because they are single replacement. So let's look at the next few examples. I think people have been struggling with the Al one. So I'm going to do that one out of all 3 of these, and then I'll leave the other 2 for you. So with the Al one, my Al and my H are what I'm comparing. Here's my H and Al. Oh, yep, that's way up there. So Al is higher. That's the one that's going to be in the compound. It's not already in the compound. So let's get it there. We're going to put this aluminum with the nitrate. And when writing that, we need to remember aluminum has a +3 charge. And so it's not going to cancel out, but the nitrate's -1. We've got a cross-drop reduce. And that's my aluminum nitrate. And then my hydrogen is left over. So I can help you with one more example if you need it. Come in, ask for it, but I think you can handle these other 2 probably. So that being said, let's move on to this other type of single replacement reactions. These just have halogens in them instead of metals. And the thing, it's just a little bit different because the halogens like to have a negative charge. So when they come over and react with the compound, this fluorine is the halogen, when they react with this compound, they're going to be reacting with the negative part, which tends to be another halogen. So halogens replace halogens is what we said here. But if we come over and we look at our list, our halogens aren't on the list. None of them are. And so what you need to remember is that because they're not in the activity series, we're going to have to use the periodic table to determine that. And way back in Unit 3, months ago, this is Unit 7 now, way back in Unit 3, we learned that the reactivity of the halogens, they were more reactive at the top of their group. And so if we look at the periodic table, the halogen group, the second to last column, those are already kind of in their own order, in their own kind of activity series there. So I'd recommend in your notes here, add them in, write them in off to the side. But if you don't find those elements in the activity series, then The answer is just look at the periodic table. And the ones higher up on that periodic table over in the nonmetal side are more active, more reactive, and the ones that are lower down are less. So when we're looking at these halogens in this first example, I'm comparing fluorine and chlorine, and fluorine is higher up. So that's the one that's going to be in my compound. And when I switch these out, the other great thing, because the halogens are all in the same column, they have the same charge. So this compound is going to look exactly the same as this compound. If this one had a 2 here, then this one has a 2 here. This one has a 3 here, this one has a 3 here. So it's just a straight swap when we have these halogens because they are nearly identical except for, the element symbol. So fluorine gets to be in the compound, and now chlorine is going to be single, but it is a diatomic like all of our halogens are, so we put that 2 on it. That's done. In our next example, we're comparing bromine and fluorine in our list. Fluorine is higher up, so that's the one that gets in the compound, and it's already in that compound. So this is a no reaction situation. So same idea as with our metals. There's just a lot more of those metals, so there's a lot more reactions you might see with them. But if it's a halogen, don't worry. Just switch it for the other halogen. Make sure that you always check the periodic table first. So that's single replacement reactions. Double replacement reactions are technically bigger and longer, but you don't have to check the activity series because in this one, this double replacement reaction, we call it the wife swap. Everyone has a partner to begin with. Everyone has a partner at the end. So yeah, someone might be switching up, but every time that someone switches up, someone else is going to have to be switching down. So we don't check that activity series, just need to find the partners and swap them. But what I want to point out before we start doing it with some real elements is how these swap. So we have our general equation right here, and I'm going to use some colors to show you that when I put this, make this switch, the first element from the first compound is going to switch to get together with the second element from the second compound. So A gets with Y as our product, and when you write that out, A is still first because it was first in its compound before the reaction. It was in AX, now it's in AY. A is still at the beginning. Y is still at the end. It was part of BY, now it's part of AY. Everything stays where it's supposed to be in that formula. It's just that they switch partners of the formula that they're in. Similarly, if we look at the other product we're going to make, I have my BX that I'm making, and I'm taking the B from my second compound and putting it with the X from my first compound. So the beginning of the second one with the end of the first one. So you need to kind of keep an eye on what your pieces are and where they're kind of starting out so you can keep them in the same relative area. So in this first example, that's all that we're really doing here is finding the pieces of the compounds we already have. We're going to break them up and make them switch partners and put them back together. But it's all just about writing compounds. So we're going to be finding and checking lots and lots of charges. So in our first example, that's not what I wanted. There we go. That's back. So in the first example that we've got here, I'm going to be breaking up my compound between the Ag and the N because these polyatomics like nitrate, NO3, are never going to break up. So we're breaking this up into pieces and we're not going to break up a polyatomic. Something like NaCl is easier because there's really just one place you can break it up. And so now I found my pieces and I'm going to rearrange them and start putting them back together. So I'm going to take this first piece, this A piece from my first compound, and the second piece from my second compound, kind of the Y part, and put them together. So that's going to make AgCl. Now when we put them together, we have to check our charges. Ag is one of those transition metals that does have a charge. It's a +1, and chlorine is a -1. So don't have to change anything. That's just AgCl. And now, when I write out that second compound, I'm going to take the B part, so Na, and put it with NO3. So Actually, I'm going to change that color there just to kind of show you a little bit better. Taking Na and putting it with NO3. Once again, checking my charges. Na is in the first column, so it has a +1. NO3 nitrate, we've seen a couple of times already, and it's a -1. So that is all that I need for my formula, is NaNO3. So these are my products of my first double replacement reaction. In this second example, we've got PbNO3, and that's where I'm going to be breaking that one up. Oops, I guess I should go back to my pen. Between the Pb and the NO3, then between the K and the I. So I'm going to put my Pb and my I together, checking my charges. I know iodine is a halogen, so that's a -1, but my Pb is a transition metal that I don't know the charge of. So we don't know what it is right now, right here, but what we're going to have to do to figure it out is go back and look at it over here. One of the most important things to remember about double replacement reactions is that in this reaction, the charges don't change. And that was pretty obvious with things like sodium in that first example, because sodium always has a +1 charge. It's always in that first column. But even for our transition metals, even though they can have multiple charges, the charge can change, it's not going to change in a double replacement reaction. So we have to look at what charge it starts with here, and then it's going to have the same charge in product side. So when we're trying to find those charges, we still can't tell what the charge is if we just look at this. We have to look at the nitrate. Each of those nitrates is a -1, and because I needed 2 of them in order to cancel out whatever lead Pb's charge is, that must mean that lead has a +2 charge. That 2 charge is why that 2 crossed over here when writing the formula. So this lead has a +2 charge. That must mean that this lead has a +2 charge as well. And in that situation, that would turn this formula into PbI2. And then the other pieces that are going together, switching colors again just to make that clear, is going to be K and then that NO3 that we saw before. And I already checked. Nitrate has a -1 charge and potassium has a +1 charge. So those are good together. So hopefully this is turning out pretty well. I'm going to go ahead. What I did in class is I stopped here and walked around and helped people. And so I'm not going to do any more examples. What I am going to do, though, is help you make sure that you know where to split up these compounds. And you don't have to write out this part, but this is the thought process that I'd encourage you to go through. And the more you write down, the less mistakes you'll make. So I'm going to go ahead and just label these charges just in case you need them. Most of them are honestly +1 and -1, except for this FeS. I know S is a -2, but Fe is a transition metal, so I wouldn't know it otherwise unless I'd check sulfur. But that -2 is going to mean that this Fe has to be a +2, so that'll be stable and neutral and cancel each other out. So I want you to try and write these 2 products and look at the patterns, the stuff that we kind of went through in that general equation and these 2 examples so far, and try your best to finish these out and come in and ask me if you need help. So I think that's it for our notes today. We did technically go on into our packet. There's 3 pages of practice, and I know it seems like a lot, but there's just a lot of space between each of the problems because we're going to ask you to do a lot with each of them. So I'm asking you to do pages 13 through 15 evens only. And for those evens, I'd really recommend you start with the 3rd step that it tells you to do, is finding the reaction type, because these aren't just going to be single replacement and double replacement anymore. This could be any of them: synthesis, decomposition, combustion. So look, find the type first, and then once you know what type it is, then follow the rules for how to predict those products. If it's synthesis, then squish it all together into one compound. If you can tell it's single replacement, then check that activity series. It might not even happen. You might have a no reaction situation, and that makes it a lot easier to finish out because you don't have to do anything else after that point. So the only other thing I want to point out about this is that we told you that we would tell you or help you with the transition metal charges, and that's right here on page 13. And these are the charges that transition metals will have if they weren't part of a double replacement reaction where you can figure them out on their own. If it's any other type of reaction and you're like, but what charge would this element have? This is what that charge would be. This is where you'd figure that out. So come in and ask for help. We'll work through some more problems. I'll check what you've done, whatever you need. But this is one of the last big ideas of our unit, so we need to put in some work on this. So good luck. Let me know what I can do. Bye.